Okay, so let's talk about a technology that feels like straight up magic. We're talking about turning a handful of regular 2D photos into a stunning, fully explorable 3D world. This is all about how deep learning is completely changing the game and redefining what's possible with just a camera. All right, here's the game plan for today. We're going to start with a little visual magic to get things rolling. Then we'll unpack the classic problem that this tech finally cracks. After that, we'll dive deep into how this new solution, NeRF, actually works, see how it stacks up against the competition, spoiler alert, it's amazing, and finally, we'll look at how it's about to reshape our digital reality. All right, let's just dive right in. We're going to kick things off with a little bit of modern-day wizardry that really sets the stage for everything we're about to cover. So take a good look at this image. I mean, really look. At first glance, it's a perfect photo of a drum kit, right? You can see the shine on the cymbals, the subtle textures, the super complex reflections in the chrome. It looks absolutely real. But what if I told you? That's not a photograph. Not really. It's a completely new view generated by an AI that only ever saw a small handful of snapshots of the drum kit from just these positions you see here. So that's the big question. How on earth can a computer create something so incredibly real from so little information? Well, the answer comes from solving a problem that has been a huge headache for computer graphics experts for, like, decades. And that challenge is called view synthesis. The goal sounds simple enough. You take a few photos of something, and then you try to create a perfect new image from any other angle you can think of. But actually doing that is incredibly difficult. You have to teach a computer to understand not just the geometry, but the physics of light itself, how it bounces off every single surface. And that brings us to this completely revolutionary approach that just changes the entire game. It's called NeRF. So what in the world is a neural radiance field, or NeRF? Well, instead of building a 3D model out of polygons, the way we do in video games, a NeRF is a neural network that basically memorizes the scene as a continuous function. You can think of it like a magical oracle. You can ask it, hey, if I'm standing right here and I'm looking in that direction, what do I see? And for any point in space, it tells you exactly the color and the density of what's there. Now, you gotta understand, this is a completely different way of thinking about a 3D scene. You're not building some clunky geometric model. Instead, the NeRF is creating this volumetric memory of the entire scene, and it's all encoded purely in the weights of the neural network. It's continuous, it's insanely detailed, and it's surprisingly small in file size. Okay, so how does this thing actually learn and then rebuild a scene? It's a really elegant process, so let's break down how this trick works. It all starts with something called a 5D coordinate. Now that sounds complicated, but it's not. It just means we tell the network two really simple things. First, an exact location in 3D space, an XYZ coordinate. And second, the direction we're looking from. That's it. That simple pair of inputs is the key to everything. Okay, so this shows the whole pipeline in action. To create a new image, we start by shooting a ray from our virtual camera through a single pixel out into the world. Along that ray, we sample a bunch of points. For every single one of those points, we ask the NeRF network our question: what color and density is here from this viewing angle? The network gives us an answer for each point. Then, we just use a classic technique called volume rendering to basically add up all those colors and densities to figure out the final color for that one pixel. You repeat that for every single pixel, and boom, you've got a brand new photorealistic image. But here's the thing. Just doing that, it's not quite enough to get those jaw-droppingly photorealistic results. The researchers behind NeRF added two crucial innovations that are basically the secret sauce that takes this from a cool idea to a world-class method. So, ingredient number one is called view dependence. See, if the network only knows the location of a point, it can't create things like reflections, because reflection changes depending on where you're standing. But by also telling the network the viewing direction, it can learn how the appearance of a surface changes with your perspective. That is how it creates that perfect shiny reflection on the chrome of the drum kit. The second secret is a really clever math trick called positional encoding. You see, neural networks on their own, they're kind of good at learning smooth, general stuff, but they tend to struggle with really sharp, fine details. It often leads to blurry results. Positional encoding is kind of like giving the network a pair of superpowered glasses. It transforms the simple coordinates into a much richer format, and that lets the network see and perfectly reconstruct all those high-frequency details, like the sharp edges on a Lego brick. Okay, enough theory. let's get to the good stuff, the results. This is the payoff, where we see NeRF go head-to-head with some of the other top methods out there. And honestly, the results just speak for themselves. On the left, you've got the NeRF rendering of this Lego bulldozer. Every edge is sharp, every little detail is crisp. Then you look at the results on the right from a previous state-of-the-art method. I mean, the difference is just night and day. NeRF captures that complex geometry with absolutely stunning clarity. Here's another one. Look at the incredibly fine, thin rigging on this model ship. On the left, NeRF rebuilds it perfectly. It understands what's solid and what's just empty space. The method on the right, though, it really struggles. It produces all these hazy, sort of ghost-like artifacts. NeRF just nails it. And hey, it's not just our eyes telling us that NeRF is better. The numbers back it up, big time. This table shows something called a PSNR score. You don't need to worry about the math. All you need to know is higher is better. And as you can see, NeRF isn't just a little bit better. It is a massive leap forward. It's a clear knockout. So the really crucial point here is that this isn't just some small improvement. It's not just a cool academic paper. This technology has massive real-world implications for how we're all going to create and interact with digital content in the future. So why does this matter to you? Well, think about it. We're talking about virtual and augmented reality that's so immersive, it's basically indistinguishable from the real world. Think about next-level visual effects in movies that can be created from a few simple photos on set. Or imagine being able to spin around a perfect 3D model of a pair of sneakers online before you buy them. We can even use this to digitally preserve priceless historical sites and artifacts perfectly, forever. The possibilities are just huge. So, if you remember one thing from all this, it should be this. NeRF is a fundamentally new and incredibly powerful way to represent 3D scenes. It's a method that's continuous, so it has almost infinite detail. It gives us unbelievably high-resolution results. And because the whole scene is just stored in the weights of a neural network, it's also incredibly memory efficient. And that kind of leaves us with this final, kind of mind-bending thought. We are really entering an era where the line between a real photograph and a computer-generated image is just dissolving completely. When we can capture and recreate our world this perfectly, from any angle we want, just from a few snapshots, what does real even mean anymore?